So again, my name is RainerWeidmann. I'm from T-Systems, and in the next couple of minutes I will give you a very short overview of our Data Center 2020 project. This project is a joint project we do together with Intel, and the goal of this project is to make energy efficiency in data centers come true in the next couple of years. And I will try to approach SDN OpenFlow from a different direction, coming from the data center infrastructure side. Before I do this, I will give you a short overview who we are. T-Systems is part of Deutsche Telekom, and you might know Mobile, for example. T-Systems cares about multinational customers, enterprise customers, and with an end-to-end ICT approach. We care about our customers' business processes in an end-to-end behavior, and including the underlying infrastructure objects. T-Systems has 20 local business units worldwide and more than 50 partnerships in the world, so we are worldwide, presence worldwide. If you go to Data Center 2020 project, we have in data centers mostly two challenges. One challenge, of course, every time is the money. And what we see in data centers, we have increasing power consumption in data centers and a steadily increase of the density in data centers, leading to the effect that we have empty floor spaces in data centers. And the second one is our environment, and in this we care about greenhouse gases, carbon dioxide emissions, and to save power in this range. So we set up the infrastructure test lab. It's a closed shop with no intersection to the production surroundings. We have no limits in this data center. In principle, you have the license to kill for the hardware you have in this test lab. And it's an ideal test bed for benchmarking and so on. The goal, as I mentioned before, is to optimize the energy efficiency, and for this we are using the PUE as defined by the green grid. It's a total facility power divided by the IT equipment power. And fields for improvement, our legacy data centers is a blueprint for Data Center 2020 to build up in a greenfield approach in the near future. And also we use our results to optimize CFD models for airflows and temperature gradation in data centers. The technical features of the data center is all a normal data center must have. It's on a floor space of approximately 70 square meters, and only to give some specials here, we have adjustable ceiling, so we can move the ceiling from 2.5 meters up to 3.7 meters above the raised floor to check the influence of the room height, the room volume on air conditioning. And we have a smoke generator for visualizing the effects in energy efficiency and of airflow. And one of the highlights is our building management systems and our measuring system, and we have more than 1,800 data points correlated to this 70 square meters. Here we have some pictures. This is a view from the meeting room. Here raised floor with the smoke. Here's the smoke generator enclosures. We have the chance to change easily between a hot and a cold light enclosure to check different setups in the data center, so that we can make some estimations what is a better system. So if we have a look in a normal data center, and in normal data centers we should have a cold and a hot light structure as a long time. And what is most important here, this is the server inlet temperature. And for this, to achieve the server inlet temperature, you have a crack unit and a fan. And even if you have this system set up, you have some weak points in your data center. One weak point is a leakage in the raised floor, usually arising from feed-throughs from network and power cabling in the back-end side of the racks. What's happening here, you have cold air coming to the hot island. So we are cooling the hot air, which makes absolutely no sense. And you have also some short circuits of the air, which is sucked from in the cold aisle again, and so it's also very inefficient. If we measure such a system, we have here 22 degrees centigrade. Here you see the Fahrenheit for your convenience. If you have 22 degrees centigrade for the servers, okay, I have to speed up. We see that we have here. Okay, perfect. So we are operating here with 6 Kelvin difference. If we make an enclosure and reducing the leakage in the raised floor, we operate here with 17 Kelvin. This means the same box has a 3 times higher efficiency. And again, by reducing the fan speed to 30%, we are saving more than 90% energy on the fan itself. And if we increase the server inlet temperature to the latest ASH recommendation, let's say 27 degrees server inlet temperature, you have a need for 26 degrees centigrade in the raised floor. And this means, for a location Munich, we can operate the data centers with less than 90 hours per year with the chillers. And this is a lot of energy savings in the cooling part of the data center. What we have also seen is that the PoE is a function of density in the racks. If we increase the density in the racks, we can improve the PoE. And up to density of 22 kilowatts per rack, it's everything working with air cooling in a rack, in these enclosures. And we can have energy savings of 20 to 30%. And if we have a look at the availability of the data center, you know, increasing densities in the racks are causing some less critical reaction times in case of any outage of the air conditioning devices. So you see that we have, without enclosures, we have no chance in principle to go to higher density because we have no cooling back. And the ideal, the optimum position is here racks with approximately 10 kilowatts per rack. Because with 10 kilowatts per rack, we are still above the UPS autonomic time, and if we didn't have back power within this time, it makes no difference if you have cooling or not. So what we have learned in phase 1, we have seen a PoE of 1.3 or better is possible with standard techniques which are already in your data center. We need leakage reduction, enclosures are necessary, and a homogeneous airflow, front to back, for example, is very important. So what's awful is if we have different airflows in the data centers, front to the side or bottom to the top, so it must be homogeneous. Then we need standardized hardware, and we can increase the data center availability with enclosures. And the savings in the data center increase with the increase of power density in data centers. And our recommendations is to reduce fan speed in crack units, increase the temperature, set up the infrastructure on demand, and increase the temperature in the racks up to more than 10 kilowatts per rack. And this must be done by increasing average CPU utilization and dynamic load sharing in data center. And this is the link to OpenFlow SDN, how this can provide this. In phase 2 of this project, we will upgrade the data center with latest CPU technology, and we will check what opportunities do we have for server and network power conservation. And we'll check some different tests. And OpenFlow SDN can support us with on a server level with caching and proxying requests until wake-up, mapping services, migration and consolidation about different data centers, for example, in an energy-aware manner. And the network device level, we have the possibility to use Elastic Tree and to shut down some different some passes in this and save money here. And we have for data center power savings, we have many existing ideas on provisioning and load consolidation and migration. And SDN can enable all this actions seamlessly without causing disruption. This is very important for data centers. And here is a picture how it can work. Here is a graph that we see the power consumption as a function of the network utilization, and also it's a need to bring down the network utilization. And here by methods of shutting off or some links and power off the links, we have the chance to move workloads in the data center to get to the situation that we have more than 10 kilowatts per rack. It's only 10 kilowatts per rack is not fixed, but we have to go to higher density in the service, and that's what it's worthwhile to think about these methods. So, OpenFlow SDN, in my point of view, has the potential to intelligently trade off power, redundancy, workload, and performance, and to enable dynamicity, automatic management, and evolvability of the data center. And DC 2020 will help evaluate potential in a realistic environment by setting up this scenario and explore it to the desired scale. Finally, the question is, how should data center networks look like in the future to support these actions? Thank you very much for your attention, and if you would like to have more information about our project, feel free to visit the internet site, the web page, and there are some white papers for download, and the downloads are shared with the data center community. Thank you very much.
My apologies to Mr. Weidmann. I held up the 5 card when he had consumed 5 minutes, not when he had 5 minutes left. That was my error. But I think you got through it. Okay. All right, Ken.